All right, diving in today, folks, we're taking a deep look at something pretty familiar, I think, to a lot of people, uh, erythromycin. It's an antibiotic I'm sure many of us have come across at some point in our lives, and we've got our hands on some really detailed scientific and technical documents outlining exactly how it's produced on an industrial scale.
Yeah, fascinating stuff.
Our mission, as always, is to break it all down and really understand, the core of how this medicine is made and why it's so crucial in healthcare.
Right from the get-go, what's really cool is that erythromycin, it's not something simply synthesized in a lab. It's actually a product of, believe it or not, a living organism, a microbe we've learned to kind of harness, on a massive scale. To be more specific, erythromycin is what we call a macrolide antibiotic. And this whole class of drugs, they're famous for their unique way of stopping bacteria in their tracks.
And how do they do that?
Well, their main tactic is basically preventing bacteria from making proteins, and they do this by attaching to a critical part of the bacteria's, cellular machinery called the 50S ribosome. So yeah, this clever mechanism is exactly what makes erythromycin so effective against a whole range of bacterial infections. It's like cutting off their supply lines, preventing them from building the essential stuff they need to function.
So we've got this microbe, this microscopic factory, essentially, that's cranking out erythromycin for us.
Yeah.
What is this little superstar we need to thank? What's its name?
The credit goes to a soil bacterium called Saccharopilospora erythraea, quite a mouthful, I know.
Yeah.
You might stumble upon its old name, Streptomyces erythraeus, in some older research papers, but yeah, that's been updated. And anyway, this little guy, it's a thread-like gram-positive bacterium. Scientists have actually managed to, over the years, develop some really high-performing strains specifically for erythromycin production,
Oh, wow.
which is really important when you think about it from, an industrial production point of view. The biological factors are all about yield and how easy it is to grow these things, and this bacterium has proven to be a pretty fantastic candidate.
So how do we actually go from this microbe just hanging out in the soil to the medicine we end up taking? That's got to be quite a journey.
That's where the magic of industrial fermentation comes in. The primary technique we use is something called submerged fermentation. Basically, we grow these bacteria in these enormous, and I mean huge, stirred tanks. These tanks are filled with this liquid, this nutrient-rich broth that the bacteria thrive in.
Like a bacterial soup, kind of.
Exactly. But here's a really crucial point. Erythromycin is what we call a secondary metabolite. That means the bacteria, they don't actually produce it while they're in their, rapid growth phase. It's more of a phase 2 kind of thing. It's like they have to get their initial growth spurt out of the way, really get settled in before they start churning out the medicine.
Interesting. So what do they need to eat? What are we feeding these bacteria to help them get to that phase 2, that production stage?
Well, it's all about a balanced diet, just like us. They need their sugars and oils, so things like glucose, sucrose, glycerol, even soybean or vegetable oils. Those act as their primary carbon sources. Then we add various organic nitrogen sources, stuff like soybean flour and peptone, sometimes with a little boost of inorganic nitrogen to round things out. And of course, just like humans, they need those essential minerals to thrive. Phosphate, magnesium, trace amounts of various metals. It's all about creating the perfect environment for them to flourish.
And the environment in those tanks, it must be so precisely controlled.
Absolutely. We can't just leave them to their own devices. We use what's called a fed batch approach, carefully controlling the nutrients they get throughout the entire process. These bacteria are what we call strictly aerobic, meaning they absolutely need a good amount of dissolved oxygen to survive and produce erythromycin. Then there's the temperature. It has to be kept within a very narrow range, 28 to 32 degrees Celsius, constantly monitored. Same thing with the pH. It's got to stay around that 6.5 to 7.5 mark. And then we've got to be really careful with the stirring. Enough to mix everything well and make sure the oxygen reaches all the bacteria, but not too vigorous. These filamentous bacteria are actually pretty delicate, shear sensitive as we call it. Too much rough mixing can damage them and actually decrease our overall yield.
So we've got our bacteria happily munching away, producing erythromycin, but now how do we separate it, isolate it? It sounds incredibly complex to get the pure erythromycin from all the other stuff in that fermentation tank. What are the biggest challenges, I guess, in getting it pure enough to be used as medicine?
You're absolutely right. It's a multi-step process. First things first, we need to remove the bulk of those bacterial cells, and we do that using either centrifugation or filtration, depending on the specific setup. Now, here's the thing. Erythromycin can be found both inside and outside the bacterial cells. So we use organic solvents at a slightly alkaline pH to extract it. If we need to get to the erythromycin that's inside those cells, we might even need to break them open, a process called homogenization.
Wow, really getting in there.
Yeah. And after that, we transfer the erythromycin to an aqueous phase at a slightly acidic pH, which essentially turns it into a water-soluble salt. Now, this allows us to either precipitate or crystallize it by carefully, tweaking the conditions. These crystals are then filtered, washed to remove any remaining impurities, and then finally dried. And because the base form of erythromycin actually doesn't dissolve well in water, it's often converted into more soluble salt forms, things like lactobionate or ethyl succinate, for the final drug products.
It's mind-blowing to think that something so intricate, with all these steps and processes, goes into making a pill that we just kind of take without a second thought. So why is erythromycin so important that we go through all this trouble?
Erythromycin, it's really a workhorse in the world of antibiotics, essential for treating a huge range of bacterial infections. It's especially critical for folks who are allergic to penicillin, or for those tricky cases where penicillin-resistant bacteria are involved. We're talking common illnesses here: pneumonia, whooping cough, skin infections, some sexually transmitted infections, gastrointestinal issues, even certain eye infections. It can also be used to prevent infections in some situations.
Really versatile.
Yeah, and it's also closely related to some other big names in the antibiotic world, azithromycin and clarithromycin, for example.
Right.
But there's a catch, and it's a big one. The increasing resistance of bacteria to macrolides, the whole class that erythromycin belongs to, is a serious problem. It's something we're really grappling with as scientists and healthcare professionals.
It's a sobering thought. So, to wrap up, erythromycin production. It's a truly fascinating and complex, multi-step industrial feat. We rely on this specific bacterium, grown under these carefully controlled conditions, to produce this, crucial medicine, which then has to go through this incredibly intricate purification process. It's widely applicable, making it incredibly important, but we're up against some real challenges with this, growing antibiotic resistance.
Exactly, and that actually brings up an important question, something for everyone listening to really ponder. Considering how intricate and demanding the process is, even for creating just one antibiotic like erythromycin, what do you think are the biggest challenges, but also the potential breakthroughs in ensuring that we continue to have effective treatments against bacterial infections in the future, especially with this, looming threat of increasing resistance? It's a big question with no easy answers.
Definitely something to think about. Thanks for listening, everyone, and we'll see you next time on The Deep Dive.
See you then.